Hi everyone. So in this video, we're going to be starting alternating series, or section 11.5 in the textbook, which is in description. And up to now, most of the series that we have worked with have all been positive terms. So now we're going to switch it up and look at a different type of series that switch back and forth. So the main question we're going to be asking in this section is, when does an alternating series converge and how can we tell? So the main idea is that an alternating series is a series whose signs alternate between positive and negative. So for example, if you can see, I wrote down just a random sequence, and as you can see in blue, that the signs are alternating, right? It goes from minus to positive, minus, plus, minus. It's going to keep alternating back and forth between plus, minus, plus, minus, plus, minus. And then there's also another common way to write the alternating series, which is right here. The first one, it's negative 1 to the n minus 1 of b sub n, where b sub n is just a positive term. Or there's also this, where you have negative 1 to the n of b sub n. So the negative 1 to the n part, it's the only thing it does is just controls the sign. And the b sub n controls the size. So the only thing the negative 1 to the n minus 1 or negative 1 to the n does, it just tells you whether the sign is plus or minus. This has nothing to do with the actual series. But this right here, the b sub n, the term, that's what actually controls the series size, if that makes sense. So mostly we're just going to be focusing on this right here, the b sub n part, and what that term is doing. That's going to be our main focus. This right here is just called an alternator. So now let's look at the alternating series test. So if a series has a form negative 1 to the n, or negative 1 to the n minus 1 b sub n, like we saw earlier, with b sub n greater than 0, basically means it's positive, then the series converges if these two things are true. So first of all, if your term plus 1 is less than or equal to the term, so b sub n plus 1 is less than or equal to b sub n, and if the limit of that term as we approach infinity is 0. So basically all this test is asking is that, are the positive terms getting smaller, and do they go all the way to 0? And if both of these are true, then we say the series converges. So just a warning before we kind of start. So just because you see a negative 1 to the n does not mean the series is going to converge. Just because like you see alternating, like the alternator, does not mean it doesn't converge, because you still have to check the conditions where to make sure that the limit is, as you approach for the term, is 0, and that the term is greater than the after term, or the b sub n plus 1. So if one of these fails, then they don't prove convergence. In fact, we'll be covering in a different video about, this is just a general idea, but there's a lot of series for the things we've gone. We haven't talked about what happens if one of them fails. Those are called conditionally stuff, which I will be covering soon. So stay tuned for that. Spoiler alert, I guess. So now let's look at how to use this test. So our step 1 is to write in the series form. It's going to be written like that, 99.99% of the time. But just in case that 0.01% of the time it's not, you know how to write it. Remember, it's just an alternator, then the series, or the term. Step 2, we check whether our term is decreasing. So this basically just means checking that if the next term, or b sub n plus 1, is less than or equal to the current term b sub n. Or you explain clearly why your expression gets smaller as n gets bigger. And then lastly, we just check whether the limit of the term approaches 0. And if both of these are true, then the alternating series test converges. The series converges by the alternating series test. So that's basically it for this test. So now let's start the examples. So we have example 1. Determine whether the series of negative 1 to the n minus 1 over n converges or diverges. So as we can see, we're going to be using the alternating series test because the series has the alternating factor, which I'll point out right here, the negative 1 to the n minus 1. that, we call that the alternating series factor. That's or the alternator. I low-key like to use the term alternator because it sounds cool, but yeah. So now let's check our test and stuff. So our step one, remember, let's identify the b sub n. So we can also rewrite the series to make it easier. So let's rewrite this, right? So we're gonna have n equals 1 to infinity of -1 to the n minus 1 times 1 over n. So we wrote that. Now it's the same thing as z, the n is in the bottom for this one. So if you want to pull this n out right, we can just multiply this by 1 over n. It's the same thing, right? If you multiply this, you'll get -1 to the minus 1 times 1 is the same thing, and divide that by n. So it's like we just factored out the 1 over n from the series. So now, as you can see, the reason we did this is so we know our term. So this is the alternator right here, or I'll underline this in blue. And in red, this is going to be our b sub n, right? So our term is going to be, or the positive part of the series is just 1 over n. Now, we need to check if this is decreasing. So we know we need to check whether your b of n plus 1 is less than or equal to b sub n. So we know our term is 1 over n. So our b of n plus 1 is going to be equal to 1 over n plus 1. So we know that n plus 1 is greater than n, right? So if we just take the reciprocal, we'll get 1 over n plus 1 is less than 1 over n. When you take the reciprocal, the signs also change. So we know that we just satisfy this condition right here. The b sub n plus 1 is less than or equal to b sub n. So let's erase this. Then I'll move this up. Now, step 3, you check whether b sub n approaches 0. So let's do the limit as n approaches infinity of 1 over n is equal to, well, we know when you plug in infinity, small number divided by a huge number is 0, so we know the limit as n approaches infinity of 1 over n is 0. Therefore, we check both things, right? Our b of n plus 1 is less than or equal to, sorry, I forgot that, 1 over n. Let's check. And we know the limit is approaching 0. Also, if you're confused on why this is greater, because think about it, right? Let's plug in like a 60. So it's going to be 1 over 60 over 1 over 60 plus 1, so 1 over 61. Obviously, 1 over 60 is greater than 1 over 61. That's why we know that this term is true. And we showed that the limit approaches 0, so we can say I'm going to write AST for alternating series test because I'm lazy. So by the alternating series test, the series over n converges. Whoops. Please excuse my handwriting. It's kind of hard to write. My iPad's slippery. So that's our final answer. So this converges by the alternating series test. So let's move on to this next example. Example 2. Determine whether the series -1 to the n minus 1 times n over n plus 1 converges or diverges. As you can see, we have an alternator again, the -1 to n minus 1. So this means we should check for the alternating series test. So now, let's rewrite this to know our term, so we can identify our b sub n. So we can rewrite this as you're going to have -1 to the n minus 1 now. Let's pull the n divided by n plus 1 out. So can we write as a multiple parentheses, so see if you n on the top. So we're going to pull that out, and we're just going to factor the whole, and pull out the bottom 2 over n plus 1. That's all you got to do. Whenever you get these type of problems, just make sure your negative 1 to n plus 1, or n minus 1, sorry, or your alternator, just pull out all the terms after the alternator. So it looks something like this. So it makes it easier because we know now our b sub n is just equal to n over n plus 1. That's our term. Now you want to check whether it's decreasing, right? So when you check whether our b sub n plus 1, or right down here, check whether our next term is less than our current term. So we know what b sub n is, so b sub n plus 1 is going to be equal to n plus 1 over, we already have an n plus 1 at the bottom, so 1 plus 1 is 2, so n plus 2, right? So now we can compare these, right? But let's plug in some values to our b sub n, because it's going to be harder to compare. It's kind of harder to compare like this way, right? Without plugging in numbers. So let's plug in numbers to this thing right here, b sub n, because when you check if this is greater or decreasing, sorry. So b sub 1 is going to be just 1 over 1 plus 1, which is 2. We have second term is 2 over 2 plus 1, which is 3. Third term is 3 over 3 plus 1, which is 4. We'll do one more. Our fourth term is 4 over 4 plus 1, which is 5. So as you can see, these are getting bigger, right? 1/2 is 0.5, 2/3 like 0.67, 3/4 is like what? 0.75, and 4/5 is 0.8. So as you can see, these terms are not getting smaller. Therefore, this fails one of the alternating series test condition. So we can write an X in blue right here. Bang. This has failed the first condition. However, we still need to check whether the limit of that term approaches 0, just in case maybe one of them. So means the limit as n approaches infinity of our term is n over n plus 1. So is equal to 0. We need to check if this is true. So let's evaluate this. So if you know, we have an n and an n plus 1, or sorry, we have an n on top and bottom, so we can divide each term by n, which will get us to the limit as n approaches infinity. N divided by n is just 1. N divided by n is also just 1. And then 1 divided by n is just 1 over n. So we have the limit as n approaches infinity of 1 over 1 plus 1 over n. So the only thing we plug in infinity is the 1 over n. We know 1 is a small number over big numbers. It's like a billion times now. It's just 0. So this is just 1 over 1 plus 0, which is just 1 over 1, which is just 1. And we know this does not approach 0, so we can write an exclamation, or sorry, not exclamation. We can cross that out too. Let me write that in blue, actually. So we know that this failed both conditions. Therefore, since we checked both, that we know that the series must diverge, right? So our final answer is, we'll have no room, so I'll just write it right here. So the negative 1 is true at the series diverges, because we know that the terms don't go to 0, so the series has to diverge. So this is one example where just because it had the sign, right, the alternator doesn't mean it converges, right? We have to check both tests. So sometimes you're going to get a case where maybe one test will be true, but the other one is not, which we will explore in another video. But for this video, just know that just because one of them works doesn't mean both of them are going to be true, right? There's always a chance that one condition works and one condition fails. So be sure to check both. Even if the first one fails, always check the second one too. So let's move on to our third example. Determine whether the series negative 1 to n minus 1 over square root of n converges or diverges. So we know we have our alternator, the negative 1 to n minus 1. Therefore, we know we can use the alternating series test. So, just like we've been doing for the past 2 examples, let's rewrite this so we can find our term. So, go ahead and try doing this without me while I write down how I rewrite this. Sorry. While I rewrite this, I can't talk. Okay, so you should have gone this. Remember, we just pulled out a square root of n from the bottom. So we know our term is going to be 1 over the root of n. So now we need to check if it's decreasing. So we need to know if our next term is less than or equal to our current term. So we know that b of n plus 1 is just going to be equal to 1 over square root of n plus 1. So we know that n plus 1 is greater than n, right? Therefore, the square root of n plus 1 is also going to be larger than our n values. And now, when we take the reciprocal, we have 1 over square root n plus 1 is less than, this should be root n. So square root of n plus 1 is greater than square root of n. So when we take the reciprocal, we know that 1 over square root of 1, I can't talk. 1 over root n plus 1 is less than 1 over root n. There we go. So we know that our term b sub n is decreasing. Now we gotta check the limit, right? So, actually, let's put a check mark here. We know this condition has passed. Now, we need to check the limit. So the limit is n approaching infinity of 1 over square root of n. So we know that when we plug infinity, it's going to be 1 over square root of infinity. Well, the square root of infinity, if you know, it's just infinity. So it's again the smaller term divided by a big term, which is equal to 0. If it doesn't make sense to you, then let's break it down, right? Let's just take the limit as n approaching infinity of just the square root of infinity, or square root of n, right? We know the square root of infinity is just infinity. Therefore, this means it's infinity, and 1 over infinity is just 0. So that's how we got that. So we checked both conditions. We saw that both of these worked. Now we can say that by the alternating series test, the series -1 to n minus 1 or root n converges. Hooray. Now, we're going to look at another idea in this section. It's called estimating the error. This one is really easy, I promise. So it just looks maybe a little complicated, but you'll see. So if an alternating, here's the definition. So if an alternating series converges by the alternating series test, then a partial sum gives an approximation to the true sum. So, and the error is really easy to estimate. So we say that if the true sum, which we denote as s, and the nth partial sum is s sub n, then the remainder is just the true sum minus the partial sum, or s minus s sub n, and the error is going to be the absolute value of the error is less than or equal to the next term, right? So basically all it's saying is that the error is at most the size of the next term. So let's look at an example. So it says, use the first 4 terms, I can't talk. Use the first 4 terms of the series to approximate the sum and estimate the error. So they're asking us 2 things. We want to get the sum of the first 4 terms, and we want to find the error. So let's do that. So let's find the 4th sum, right? So for that, we need to plug in our values, right? So we can rewrite this as n equals 1 to infinity, -1 to n minus 1 times 1 over n. Remember, we just pulled the n out. So now let's write it down. So s sub 1 is just 1. Remember, we plug in a 1, right? 1 divided by 1 is 1. So 2 is just a half. Third is just third. Fourth is just 1/4. Sorry, this is wrong. These are the values. Whoops, not the partial sums. Because the S means it's a sum, right? So S sub 2 would actually be 1 minus a half. So I'm sorry, I miswrote that. So we just plugged in the 4 values. So now let's compute the term. So you write S sub 4 equal to, remember this is alternating, so 1 minus 1/2 plus 1/3 minus 1/4. So so just remember, we're not adding all these. Remember, this is an alternating series, so the signs are going to be alternating. So lucky for you, I already did the calculation, right? So in fractions it's 7/12, or decimal form it's 0.5833. So that is our first 4 terms, and that's the approximate of the sum for the series. So that's our first 4 terms. Now we want to estimate the error. So in the theorem, it said the error is always going to be less than or equal to the next term, right? So the error is less than or equal to b sub n plus 1. Well, here we know that when n was 4, we got 1/4, right? So when n equals 5, we're going to get 1/5. Therefore, we know that the error of the 4 term, remember, it says r sub n, so we just plug in the 4. It's less than or equal to the 5th term. So what is the 5th term, right? So in this series, we plug in a 5, right? Or we can do it right here, down here. A sub 5 is equal to 1/5. So it says that the approximation error is at most 0.2. So that's all it is. That's all you got to do. So it's basically just saying that the error is always going to be less than or equal to the next term. So that's all you have to do. Just remember to not plug in a 5 here. Instead, I write the 5 because you see that's the error for the 4th term. So we plug in a 4 for, well, we're not plugging in, but we just write 4 less than or equal to for the n plus 1, then we add the 5. I'm sorry, this is complicated, but it's just saying that the error is always going to be less than or equal to the next term. So there you have it. There's your approximation for the first 4 terms, and here's your error for the 4 terms. So quickly, let's go over a recap. We know an alternating series is a series which signs go back and forth, so plus minus. And we know that the series is going to converge if b sub n, or your term, is decreasing, and the limit, and when you take the limit, it approaches 0. So remember to check these 2 conditions. If one of these fails, they do not prove convergence, and we will be exploring the idea later. And then, if the series converges by the alternating series test, then the error is going to satisfy that, and here's the formula, that the next term is basically, the current term is going to be less than, the error for the current term is always less than or equal to the error or the next term. So that is the big idea for this section, and hope you learned something, and I hope you have a great day. Thank you.